Ever wondered what's inside your smartphone, your laptop, or even your car that makes it so smart? The answer is tiny electronic brains called microchips. These things are everywhere, powering our digital world, but how are they even made? It's one of the most complex manufacturing processes on the planet, but today, we're going to break it down into simple steps. So, get ready to dive into the incredible world of a semiconductor factory. It all starts with something surprisingly common, sand. Well, not just any sand, but sand that's rich in silicon. This silicon is purified to an incredible degree, like 99.999999999% pure. Imagine a swimming pool of water with just a single grain of sugar in it. That is how pure we're talking. This ultra-pure silicon is then melted down in a crucible at over 1,400 degrees Celsius. Once it's molten, a tiny seed crystal is dipped into the liquid silicon and slowly pulled upwards while rotating. As it pulls away, the silicon atoms attach to the seed, copying its crystal structure. What emerges is a massive, single crystal cylinder of silicon called an ingot. These ingots can be over 6 feet long and weigh hundreds of pounds. It's basically the most perfect and probably most expensive log you've ever seen. Next, this giant silicon log needs to be sliced up. Using a diamond-edged saw, the ingot is cut into incredibly thin, perfectly flat discs. These are called wafers. They're usually about the thickness of a credit card, but much more fragile. These wafers are the foundation, the canvas, upon which we'll build our microchips. Before we can start painting, though, the wafers are polished to a mirror-like finish, making them one of the flattest surfaces ever created by humans. Any tiny bump or imperfection could ruin of chips. Now, we enter the clean room. This is where the real magic happens. Clean rooms are thousands of times cleaner than a hospital operating room. A single speck of dust is like a giant boulder in the world of microchips, capable of destroying off circuits. People working in these clean rooms have to wear special head-to-toe suits, often called bunny suits, to prevent any dust, hair, or skin flakes from contaminating the environment. The first step inside the clean room is creating a non-conductive layer on the silicon wafer. This is done through a process called oxidation. The wafers are placed in a high-temperature furnace with oxygen, which causes a thin, uniform layer of silicon dioxide, basically a type of glass, to grow on the surface. This layer acts as an insulator, preventing the electrical currents from going where they're not supposed to. With our insulated canvas ready, it's time for the most critical step, photolithography. This is essentially like a form of photography, but on a microscopic scale. First, the wafer is coated with a light-sensitive chemical called photoresist. Think of it like the film in an old camera. Then, a blueprint of the chip's circuit design called a mask or a reticle is placed between a light source and the wafer. This mask is like a stencil, with the intricate patterns of the circuits etched onto it. A beam of ultraviolet light is shown through the mask. Where the light passes through, it hits the photoresist and causes a chemical change, making it soluble. The areas obscured by the mask's pattern remain unchanged. After the exposure, the wafer is washed in a developer solution. This solution washes away only the exposed, softened parts of the photoresist, leaving behind a perfect stencil of the circuit pattern on the wafer. This process of coating, exposing, and developing is repeated dozens, sometimes hundreds of times, to build up the complex, multi-layered structure of a modern chip. Each layer has a different pattern, and they all have to align with each other. The next step is etching. Now that we have our photoresist stencil, we can start carving into the wafer. The wafer is bombarded with a plasma of superheated gases. This plasma eats away at the silicon dioxide layer, but only in the areas that are not protected by the photoresist. Once the etching is done, the remaining photoresist is stripped away, revealing the newly etched patterns in the glassy layer beneath. We've just carved the first layer of our circuit. Now we need to create the transistors, the tiny on-off switches that are the fundamental building blocks of any chip. To do this, we need to introduce specific impurities or dopants into the silicon to change its electrical properties. This is done through a process called ion implantation. A machine accelerates ions of elements like phosphorus or boron to incredible speeds and fires them at the wafer. These high-energy ions blast through the surface and embed themselves into the exposed silicon, but are blocked by the remaining silicon dioxide layer. This doping process creates regions that are either rich in electrons, called N-type, or regions that are lacking electrons, called P-type. Where these N-type and P-type regions meet, we form our transistors, billions of them. And we're still not done. Modern chips are like skyscrapers with many levels of circuitry. We need to connect all these billions of transistors together. So, we start building upwards. A thin layer of metal, usually copper, is deposited over the entire wafer. Then, we use photolithography and etching again to carve out the intricate network of wires that will connect the transistors on that level. After the metal wiring is patterned, another insulating layer is added on top. Then we repeat the process. Add metal, pattern it, add another insulator. This happens over and over, creating a dense, three-dimensional maze of interconnects. It's like building a city with dozens of levels of roads and highways, all packed into an area smaller than your fingernail. Once all the layers are complete, the manufacturing process on the wafer is finally finished. But we don't have individual chips yet. We have a single wafer with hundreds or even thousands of identical chips printed on it. Now it's time for testing. A machine with microscopic probes touches down on contact points for each individual chip or die on the wafer. It runs a series of electrical tests to see if each one works correctly. The ones that fail are marked with a dot of ink. It's not uncommon for some chips to have defects, so this sorting process is crucial. After testing, a diamond-tipped saw cuts the wafer apart, separating all the individual dies. It's like cutting a sheet of cookies into individual squares. The good unmarked dies move on to the final stage, packaging. The bad ones are discarded. The fragile silicon die is incredibly delicate. It needs a protective home. In the packaging stage, the die is mounted onto a substrate, which has tiny metal pins or balls on the bottom that will eventually connect to a circuit board. Then, incredibly thin gold or copper wires, thinner than a human hair, are bonded from the contact pads on the chip to the pins on the substrate. This is what allows electrical signals to get in and out of the chip. Finally, the entire assembly is encapsulated in a hard plastic or ceramic casing to protect it from moisture, heat, and physical damage. This is the black rectangle with metal legs that we recognize as a computer chip. After one final round of testing to make sure everything still works after packaging, the chip is finally ready to be shipped out and installed in our favorite devices. So, from a grain of sand to a complex electronic brain, that's the journey of a microchip. It's a process of unbelievable precision involving physics, chemistry, and engineering at the absolute limits of our technology. Every time you turn on your phone or computer, remember the incredible microscopic city of transistors and wires working tirelessly inside. It's truly one of the wonders of the modern world. Thanks so much for watching. If you found this journey into the world of semiconductors fascinating, make sure to hit that like button and subscribe for more deep dives into the technology that shapes our lives. See you in the next one.